All right, we're back. Third video. Oh, that's me right there. We're at number 16. We're going to get there to the end if it takes 20 videos, I'm going to get to the end of this. All right. So in number 16, the graph of a function is shown in the figure at the right. And for that, you're supposed to integrate from 1 to 7. And how we would integrate this from 1 to 7 is we'd find the area under the curve by just using geometry shapes that we know. So what are some geometry shapes from 1 to 7 that we could use? So first, from 1 to 7, I see a long rectangle along the bottom, and that is 1 by 7. So I take this long rectangle right here, and 1 by 7 is 7. So I'm going to write down, I'm integrating from 1 to 7, f at x dx. And I see a long rectangle that's 1 times 7, or 7. So there's the long rectangle. I also see a triangle here. Now I'm not going to go way to the bottom. So this triangle right here, half the base times the height. So that's 1/2 times 2 times 1. And then I see another triangle here, half the base times the height. So that's half times 1, and the height is 2. So if I had to simplify it, then I will. But if I don't, that's a great answer. But if I had to simplify it, then this is what it would look like, and I would get the answer 9, just by finding the area under the curve. Did I do that right? I think I did it wrong. I think I made a little mistake. So from 1 to 7 is not 7. Did you catch that mistake? So from 1 to 7, it's 6 across. So this should have been 6, which changes the 9 to an 8. I just looked at the answer key real quick. So this should be a 6 because it's 6 wide and 1 up. So it's a 6, so that makes this an 8. All right, next part of the question. What's the average value then of the function? Well, the average value from 1 to 7, you have to integrate. Well, I just did. So the numerator is 8. And then you divide by the difference of the bounds. So if I do that, I already have the numerator because this is the numerator. And that answer is 8. And then I divide by the difference of the limits, which is 6. So then I get 4/3. Part C. Determine the answers to parts A and B if the graph is shifted 2 units up. So if I shift everything up 2 units, it creates a bigger rectangle. And so you have to add that rectangle 2 units up. And so that rectangle 2 units up would be 2 by 6. So I'd have to add 2 times 6. That rectangle, 2 by 6. So if I move everything up, it would create a rectangle that would be 2 by 6 that you'd have to find the area of and add it. So that's 12 plus 8. And then how would that change the average value? You now use 20, and it would be 20 over 6, or what goes into both? 3, 4, 2, right? Just that. 10 over 3. Done. Good thinking question. Number 17. In number 17, we're getting there. We're going to do Riemann sums and trapezoidal rule to integrate 17 and 18. So let's do that. I hope this is simple. So I'm integrating from 0 to 8, x cubed dx, n is equal to 4, and I'm going to use a midpoint Riemann sum for part A. And I'm going to use the trapezoidal rule for part B. So let's see what that would look like. So I'm integrating this, doing a midpoint Riemann sum and a trapezoidal rule. Both of them would start the same way. So I'm going to write down what I'm doing to begin with. And then I have to find the width by going the top limit, subtract the bottom limit, divided by 4. So each rectangle and each trapezoid has a width of 2. So that's how it starts. I can do both at the same time, right? Maybe. Now the trapezoid starts this way. 1/2 times the width. Now for a midpoint, I'm finding the middle x value. So if it has a width of 2, the middle x value I first plug in 1, then I plug in 3, then I plug in 5, and then I plug in 7. I don't even want to simplify it, but that's it right there. So these give me the heights of each rectangle, the middle x value, and you plug it into the equation. For a trapezoidal rule, where the width is 2, I'm going to use different numbers. So the first height is 0, and then I double, and again I'm counting by 2's. So it's going to be 2, I double, I'm going to use 4, I double, I'm going to use 6, and then the last one I don't double. So it's just 8, and you have it. So that's a Riemann sum and a trapezoidal rule. And there's no need to simplify that. That would be silly. Unless if you had a calculator, you could just type it in. But that's not where we're at. Number 18. Same question, but with a different equation. So from 0 to 12, negative root x dx, n equals 3. And again, we're going to use a midpoint and a trapezoidal rule. So step 1 here is to write down what the width is. Sure, I got this straightened out here for you. So to find the width, the top limit, subtract the bottom limit, divided by 3. So the width of each rectangle, or the width of each trapezoid, is 4. So in part A, I set this up from 0 to 12, negative root x dx. What does it equal approximately using Riemann sum? So the width is 4. So the first interval goes from 0 to 4. So midpoint would actually be 2. The next midpoint would be from 4 to 8. So you'd use 6. And then the next one, and really you're just adding 4 from the midpoint, would be negative root 10. And that would be is that enough? I need one more. So from 0, no, there's 3 of them, sorry. 3 rectangles, there they are. Done. No need to do anything else with it. Now for part B, the trapezoidal rule, how would that change things? Well, the formula is 1/2 times the width. So I'm going to use different numbers. I have to start with 0. And then I double. And I'm going by 4s. So I got to plug in 4. And then I'm going to plug in 8. And then I'm going to plug in 12. But 12 will not be doubled. So for the trapezoidal rule, the first height and the last height are singular. And the middle heights are shared. And so that's why they're doubled. And those are the exact heights, and just leave it the way it is. Notice I'm not even writing 0 down. Like, just follow the pattern and don't overthink it. Number 19. A pasture is bounded by a river and 2 fences, as shown in the figure. Approximate the total square yardage of pasture using a midpoint Riemann sum using 5 equal subdivisions. So if I do that, and this is 0, there's 500 yards of fence. So the width would be 500 take away 0 divided by, how many are we using? 5. So that means the width of each one would be 100 for part A. So it's like 500 take away 0 divided by 5. So the width of each one would be 100. And so we'd start with 100. Midpoint would mean that I'd have to use 50, 150, 250, and so on. Let's see what that would look like. Oh, and here's the table of values. So I'd have to use 50, so that's 210, 150, that's 190, 250, 120, 350, 60, and 450, that's 40. So that's using the middle. So the first interval goes from 0 to 100. The middle value I use for the height. So I keep using the middle value all the way across for the height. This is what it looks like. And then the second part was a trapezoidal rule. So let's look at that. For the trapezoidal rule, n equals 10. So we have to change this a bit. So it's going to be 500 divided by 10. So that's 50. So now the width is 50. And the trapezoidal rule is 1/2 times 50. And then every 50 is a height. So I got to go all the way across. It's super long. And make sure you double. So the first one, 250. But then you double 210. Then you double 190. And then you double 190. And then you double 170, you double 120, you double 80, you double 60, you double 60, and you double 40, and then the last one, 0. This is what it would look like. So it's 1/2 times 50, and then every 50 is a height. So the first height and the last height are singular. All the rest are doubled. Just follow the pattern all the way through, and you have your answer. All right, that was number 19. Number 20 and 21. So number 20, two men in a search party begin walking from search headquarters at the same time. One man walks north. And they're walking north at 4 feet per second. The other one is walking west at a rate of 3 feet per second. After both men have walked for 1 minute, find the distance separating the two men, the rate at which the distance between the two men are changing. Okay. So here's my attempt at a drawing. So the search headquarters, one is going north and the other is going west. If I connect it, you can obviously see a right triangle. So when t equals 1 minute, if you're going 4 feet per second, then there's 60 seconds in a minute, so it's 240 feet. The other one at 3 feet per second, you're going to go 60 times 3. That is 180. And then I want to find this distance right here. I'll call it c. So to find c, it's the square root of 240 squared plus 180 squared. Is that a nice, easy answer? I'll just give it to you if it is. Yep, it's 300. So that's one question. How far are they apart? This is just the Pythagorean theorem, and you just square root it to get c by itself. The next part is calculus. What's the rate of change of c? So to do that, we need to write a squared plus b squared equals c squared. There are no constants here. These are all changing over time. So I have to take the derivative immediately. So the derivative of a squared is 2a, and then you write down the derivative of a with respect to time. Then the derivative of b squared is 2b, and then you write down the derivative of b with respect to time. And the derivative of c squared is 2c, and then it needs the hook, the derivative of c with respect to time. So because we're doing an implicit derivative, where we're taking the derivative with respect to time, it needs these hooks every time you take the derivative with the variable involved. Now we substitute in. I know A is, I got to label it. Let's label this A and this B. So that means A is 240. And the rate A is going is 4 feet per second. B is 180, and the rate B is going is 3 feet per second. C, we just said, was 300. And this is what we're looking for. So all the other numbers you plug in and then solve it. So if you want to make life easier, we could divide 2 out of everything. That gives me what? 800, 960 plus 540 add these together. That's 114. That's 1,500. So it is going to go nicely. And then divide by 300. So 1,500 divided by 300, and the answer is 5. And it's feet per second. I won't even make you write a sentence. So that's what you're looking for. At that time, what's the rate of the rate that's the difference between them? And the rate is changing at 5 feet per second. 21. Last one. So for 21, use the graph of the derivative at the right. And these are such good questions because they're challenging conceptually. And the more we practice, the stronger we'll get, I hope. So when I look at that graph, I want to do a first derivative number line. There are arrows at both ends. So what I look for are the x-intercepts. -3, 0, and 3. That's what I'm doing. Okay? The x-intercepts. Then I look, is it above or below? So it starts below, that's negative. And then from -3 to 0, it's above, that's positive. From 0 to 3, it's below, that's negative. And then from 3 on, it's above, which means it's positive. So I just did a first derivative number line. For the function, we have a minimum, we have a maximum, and we have a minimum. So this tells me increasing and decreasing for the function. Now, I also want to do a second derivative number line. Now, for the second derivative number line, I'm going to look for turning points. So we have a turning point at -2, and we have another turning point at +2. And then I'm looking for increasing and decreasing. So first it increases, which is positive. After -2, it decreases. And then it increases again after 2. So I got positive, negative, positive, increasing, decreasing, increasing. And so I'm going to use these to graph. So part A says to graph the second derivative. So I'm going to do that. I know I need to count to, using the second derivative, I need to at least count to 2 and -2. That's good. And what I'm looking for this, positive, negative, positive, it's above, it's below, and it's above. These are x-intercepts. So -2 and +2 are x-intercepts. It's above, and then it's below, and then it's above. If I really want to be more accurate, look, where's the point of inflection here, where it goes concave down and then changes? At 0, that's where this would turn. So at 0, this represents the point of inflection of the derivative graph. But most importantly, this reflects the number line. It's above, then it's below, and then it's above after 2. So there's the graph of the second derivative. Label it. Now I want to do a graph of the function itself. So I'm going to do it right here beside the number lines because I'm going to use both. For this one, I need to count from -3 to +3 at least. Now, what things am I looking for? So notice here I labeled some things here. At -3 is a minimum. At 0 is a maximum. So we're going to put a maximum here. Let me put a minimum. I don't have any point to start with, right? So at -3 and at +3, those are minimums. And then I just have to worry about concavity. So I have a minimum at -3, a minimum at +3, and I have a maximum at 0. The concavity, up to -2, it's concave up. So I'm going to go concave up. And then after -2, it's concave down. See if I can make this kind of smooth. And it's concave down up to 2, and then after 2, it's concave up again. Make sure this matches. So first of all, it decreases, and then it increases, and then it decreases, and then it increases. This is, and there's a minimum, a maximum, and a minimum. Concave up, concave down, concave up, and this function matches this. This picture might be shifted up or down, but this is what the picture looks like. And then the picture of the second derivative. That's it. You did your homework. Mr. G Math over and out. That's it. Only 3 videos. I'm proud of you for doing your work. Until next time.